1 minus e to the negative kt. Or you could write it as, in terms of time, 1 over k times the ln of 1 over 1 minus the conversion. So I can give you a conversion, I can ask for a time, right? That would be this equation. Or I can give you a time and ask for a conversion. That would be this equation. So obviously this one's pretty simple. We had A plus B goes to C. It's about as simple a reaction as you can have. B was in excess, so it didn't even show up in the rate equation. So really you just had A goes to C. Pretty simple reaction. And then it was batch, so that means it was constant volume. And so it's not that hard to get to this point. And you get a very simple rate equation when you're done, or not rate equation, but you get a very simple expression of conversion as a function of time. So that was a batch reactor. What do you guys think is next?
CSTR?
CSTR. Okay, again, we start with the mole balance. So there's no accumulation term here, right? Because it's a continuous third tank reactor, so we treat it at steady state. We have flow in and flow out, and of course we have the reaction. And so we can write it either in terms of flow rates, or more conveniently, right, we always write things in terms of conversion. So that's that form. So we'll draw our picture now. Okay, so what phase is the reactor? Liquid, right? That's why I drew that little squiggly line. And again, we'll take the same rate law that we had. Okay, so the stoichiometry section, that's where we are now. Do we have a constant volume reaction? Yes. So yeah. And then we have, I'll move this. Concentration is equal to flow over volume Okay? Any questions there? I started with the definition of concentration. In terms of a flowing system, it's molar flow rate divided by volumetric flow rate. If the volumetric flow rates aren't changing, then that drops out. That just becomes V0. And then we just continue to solve. This is from the stoichiometric table, right? And then we get a concentration in terms of conversion. You'll notice that it's the same as a batch reactor, right? And so again, now we can take this and that, and now we can put them together, and you get FA naught times X divided by So I divide it by the rate law, but as I'm writing the rate law, I go ahead and substitute in the concentration of A in terms of conversion. Okay? And I started with the material balance in terms of conversion. So now everything's just in terms of conversion. And so you can, again, you can simplify a little bit. And so now I can also write so this is a little bit different than what we had earlier, and we see two changes now. What's this guy? Right. We don't have time anymore, but now we have residence time. You notice it's still multiplied by k, right? And then that's equal to x over 1 minus x. So what are the units on residence time? Inverse of k. I like that. That's a good answer. No, that's not correct. What are the units on residence time? Time?
Time.
Right, yeah, time. What are the units on k? Inverse time. For what? For what type of rate law? First order, right? So if I had a second order rate law, do you think there'd be a concentration term over here? Yeah, you betcha. There better be, because this is dimensionless, right? So if I give you a second order rate law on a test, you guys aren't just going to flip through your notes and go, oh, that's the equation to use, I'm done. You'll have some notes. You'll have a couple pages. Because if you got to look through 50 pages of notes, you're already in bad shit. It forces you to review too. I always like the crib sheet because by the time you guys make the crib sheet, you studied for the test. You might not have realized it, but kind of the point.
Excuse me?
Yes?
So why the volumetric flow rate is the same element as often?
Okay, no, that's a good question. So why is the volumetric flow rate the same? If it was different, then I'd be depleting the amount of volume in the system, right? So that would be not steady state anymore. So you operate these things at conditions of steady state. And then the other reason why it's the same is because this isn't a gas phase system. So a gas phase system, this might not be true. And there, it would be depending on whether or not you wanted the pressure to change, but again, that's not, For a gas phase system, what depends is I don't want the pressure to change. It's not that I don't want the volume of liquid to change. Now I don't want the pressure to change. The only way that the pressure won't change is if the volumetric flow rate is changing for certain reactions. Namely the ones that are like A goes to 2B. Right? That means I've got to flow out faster. Otherwise the pressure will change inside the CSTR. So for a liquid phase system, again, at steady state, the amount of volume in this unit can't change. So the volumetric flow rates better be the same. For a gas phase system, again, the pressure can't change. And so that means that the volumetric flow rates might change. Okay? Does everybody get that? All right, so CSTR does not mean constant volume. That's only true if you have a liquid CSTR. Yeah?
Where did tau come in the picture?
It's the definition, it's the volumetric flow rate, and then the total volume.
Oh, that's tau.
That's tau, yeah.
Oh, so that's total volume.
Yeah, the residence time is volume over flow rate. Right, that's how you get time. If it's 10 liters and 1 liter per second, then you're good at 10 seconds. Good questions, though. But yeah, steady state has two completely different implications depending on whether the CSTR is liquid phase or gas phase. Either way, it's at steady state, but it changes every day. So I can continue to rearrange this, right? If you want it in terms of conversion, you can do that. You get tau k over 1 plus tau k. So again, I can give you a residence time, which is just another way of saying I can give you a volume and ask you to tell me a conversion, right? If I give you a volume and a flow rate, you can tell me the conversion, or or the other way around. I can give you a conversion and ask you to tell me the volume of the CSTR. Okay, those are the two types of questions you're most often going to get.
Will we be given volume or like volumetric flow rate?
Again, it depends. So if I give you a conversion, I'm asking you to tell me the volume. That's where you get in the title reactor design, right? Is you have to tell me the size in order to get a specified conversion. Or
Will we be
Would you
given-
still need flow rate?
yeah, I still have to tell you flow rate. Yeah. So just one more expression that I can also write tau in terms of concentrations, which are changing. Because sometimes you might be asked, what's the outlet concentration going to be, right? That's just another way of asking you what's the conversion. So not everything's going to be just, simple conversion, volume, volume conversion. But with that information, you can calculate a large number of things about the system. All right, so now we're going to talk about something called the Dom-Kohler number. That's dA and that's what it's equal to. So there's something a little bit different than the ones that we've seen earlier, right? What's different about this?
Initial rate law?
It's the initial rate. Yeah, this isn't just the rate law. This is just the initial rate, okay? So you can calculate this pretty much right away, right? Now, I mean, if you have a volume, right? You can just calculate that right away. Because you're always going to be given, usually going to be given initial conditions.
Is that the volumetric flow rate or is it total volume?
That's the total volume. Okay, so this is rate of reaction at inlet, which is another way of saying at initial time, right? If you're thinking about a batch reactor, divided by the inlet flow rate. So another way to look at it is it's a reaction rate over a convection rate. So for a first order reaction, dA is just equal to K times Ca naught times the volume divided by the volumetric flow rate times Ca naught. Yeah.
So by putting over the convection rate, are you assuming turbulent flow?
I mean, what this relates to, like a lot of these, this isn't a dimensionless, but like a lot of these, it's to give you an idea of what type of reaction you have. I mean, if you're close to a high value on this, then essentially what it means is that you have a very slow flow rate, right? So it doesn't assume things about turbulent or laminar flow or anything like that. It's simply, I mean, you'll see how it's used as we keep going. Yeah.
If it doesn't assume turbulent flow, then how does FAO represent convection at all? So you don't know if there's any sort of transverse motion.
No, that's true, but yeah, I mean, I guess in that sense, you would have to assume, like you said, that it's mostly turbulent, which is usually the case, because, I mean, chemical reactors aren't run at laminar flow conditions. But yeah, I mean, I wouldn't get too caught up in reaction rate versus convection rate. Okay, so what is this?
Residence time.
Residence time, CA naught cancels, right? So I just get K times the residence. All right, let's do it for a second order reaction. Again, you have the same expression. Now only one of the CA naughts cancels. So I get so if I increase the Dom-Kohler number, does conversion go up or down? Up, right? Think about it. It's faster reaction or more volume, or I slow down the flow rate. All three of those are going to increase the conversion. And similarly, if I decrease it, same thing. So if dA is less than or equal to 0.1, then conversion is typically about the same. Okay? And similarly, if dA is greater than 10, then the conversion is greater than about 0.9. In fact, I can write out the Dom-Kohler number in terms of conversion. The other way around. Conversion in terms of the Dom-Kohler number. Again, this is for a first order reaction. So Dom-Kohler numbers, it's a useful way of describing a system, right? Based in terms of how much is happening within that system. Conversion is another way of doing the same thing. But you'll see other places that Dom-Kohler is used. It's kind of like a shortcut. Kind of like epsilon and delta are convenient shortcuts. So is the Dom-Kohler number. So let's look at CSTRs in series. So we have a first order reaction, and we're going to say no volume change. Okay? Any questions about the nomenclature? We're feeding in the volumetric flow rate here.